In this video, we're going to talk about the concept of flux. And flux gets a capital Greek letter phi. And depending on the type of flux you're talking about determines what type of subscript it's going to get. Now, because we're talking about electric fields, we're going to use phi sub e, okay, for electric flux. There's also magnetic flux, and we can even use gravitational flux. Now, flux simply means to flow. So what the heck is flowing? Well, the what, which is flowing, is the field. And the field is basically going to be passing through an area. We define flux, phi, in its most general form. I shouldn't say its most general form, in its simplest form, where everything is constant and ideal. Then we could say that the flux, any flux, is equal to a field times an area. Now in our case, we're going to say that phi sub e is just equal to E times A. But there's some implications here with this particular designation, this way of writing it, and we're going to talk about that more a little bit later. So for the most part, this is what we're going to be using, but only after you have ensured that the appropriate conditions have been met to be able to use flux in this form. Now, flux is going to be a central theme to our next major topic, which is Gauss's law. Flux is really just an adaptation of our force perspective. And this is what I mean by that. Non-contact forces use fields to describe the action at a distance. In other words, how can two objects which never come into contact be exerting a force on each other? We looked at this a lot more in mechanics. So, at the heart of flux, at the core of what we do with flux, is fields. And fields arise from forces. So, in our case in electricity, the electric field is defined by the electric force divided by the test charge. Let me point out that, here is force, right? We got force, and that's our force perspective. So the field is just another way of looking at forces, but whenever we don't have that second object to have a complete interaction, so it's almost like having half of an interaction, we still need that other thing to interact with our source in order to create a force. So the electric field is just one way of addressing forces whenever we don't have an actual force interaction. Okay, so we have the electric field is defined by the electric force divided by the test charge. And now what I want to do is I just want to multiply by 1. And to multiply by 1, I'm going to choose to do it as area divided by area. All I've done was multiply by 1. That's legal. That's allowed, algebraically speaking. And so if I do that and I move one of these a's to the other side, then we're going to get E times A is equal to the electric force times the area divided by Q naught. And E times A is how we defined flux. So we could just say that flux is equal to Fe times A over Q naught. Now, this is a woefully incomplete description of what flux is. This is not the way we're typically going to look at it. And a little bit later in this video, we're going to pick up from where we left off here with all of this expression, and we're going to massage it into the form that you would see in your textbook. When it comes to using Gauss's law, which we're going to talk about in a little bit, but one of the main concerns with Gauss's law is that for our purposes in AP Physics C, we're only going to use it in highly symmetric situations. And highly symmetric is really key here. Now, what does it mean to be highly symmetric? Well, highly symmetric is going to mean that the field is everywhere perpendicular to what we call the Gaussian surface. The other thing that that means is that the field is constant everywhere across the Gaussian surface at the particular distance from our source that we're considering. Okay, so the idea of flux, there's a couple of important things we have to look at here. The idea of flux is E times A, and we're basically saying that this is the amount of field which is enclosed by an area. And we also talked about the field flowing. So you can think about this as being like a window in a wall. Okay, so if we have a window right here in the wall, and we've got air blowing past this open window, but it's blowing parallel to the wall like this, then no air is going to go through the wall. And that means there's basically no flux. There's nothing flowing through that opening. On the other hand, if the air is moving perpendicular to the wall, then there's a lot of air which is going to be flowing through that window. And of course, those are the two extremes, and you can also include other angles. So let me show you the types of situations that we're trying to avoid, because this is our basic idea: air moving perpendicularly through the area. I'm sorry, not air, field moving perpendicularly through an area, and it's constant all the way across it. But let's look at a situation where that's not true. So let's say we have a point charge. That point charge creates, and we'll say it's a positive point charge, and I'm only going to draw half the field, but it creates an electric field which is radial to the charge. Okay, now if I select a flat sheet, a plane of some sort, then it's going to look something like this. Now, the electric field that's passing through that, there's two things that are happening here. First of all, you'll notice that the electric field being radial, the further away you get, the weaker the field gets. These field lines are getting further and further apart as you go outwards in both directions. The electric field, as it comes through, is getting spaced further and further apart when we look at those individual field lines. So we have a high concentration of field lines here, and we have a low concentration of field lines the further we get from the source. And so that's going to violate the first thing that we're trying to accomplish, and that is that we want the field to be constant. It has to be a uniform field if this is going to be easy for us. The other thing that needs to be taken into account is that not only is the field getting weaker the further away from the source that you get, but the angle that the field makes relative to the surface is also changing. It's not all perpendicular everywhere. See, we want that field to be perpendicular everywhere. And so we talk about the normal vector, and the normal vector just means that we're perpendicular to the surface. So even though area itself is not a vector, we're going to define some direction here and say that the perpendicular to the surface, if we have a little surface element right here, perpendicular to that is going to be normal, mathematical definition, and then it's positive away from the surface or away from the source, and it's going to be negative towards. So our two problems here is that the angle is changing everywhere, and the electric field is getting weaker the further you get away from the source. So that would not be a very good use of electric flux. Now, this doesn't mean it's impossible to solve this problem, because you could do this, but it's not ideal, and that's what we're looking for, the ideal cases. So let's take a more formal approach to discussing flux here for a minute, electric flux. And so we know that flux, phi, is defined by E dot A. Now, as a reminder, dot represents the dot product or the scalar product. And in functional terms, the dot means that we have a cosine of phi. Now, the example that we took from mechanics of this was the definition of work. Work was defined by FD cosine of phi, where phi was the angle between two vectors. And that's different from theta, because theta is the angle between a vector and one of the axes of your coordinate system. Now, whether you call it phi or theta in the end doesn't matter as long as you know what it represents. But we like to use phi so that we have a visual reminder we're not talking about an angle between a vector and an axis. We're talking about an angle between two vectors which have been placed tail to tail. So, what are the two vectors that we're talking about here? Well, we have the electric field vector right here, and then the area has a normal vector. Okay, this is what we were talking about up here. So the normal to the area, and that's going to make that a vector. Okay, so we end up with a scalar quantity when we're talking about flux. And of course we like scalars because we don't have to worry about negative signs the same way we have to worry about negative signs in direction when talking about vectors. Practically speaking, what the dot tells us is that only the component of E, which is parallel to the normal vector or perpendicular to the surface, is going to be important and is going to be used. Now, the A represents the Gaussian surface. This is going to be the area of our Gaussian surface. And we'll talk about that more whenever we get into Gauss's law. And finally, when we look at E, what we're looking at is that the electric field is constant in that area. If the surface is an arbitrary blob, then you need to divide the balloon into an infinite number of infinitely small areas which can be considered flat. Now, that is an absolutely appropriate application. And if you can do that, then you have your field, which is basically perpendicular everywhere, or at least you can measure the field relative to the normal, which is perpendicular to that surface. Now, how is it that you can consider it to be flat? Well, I use the Earth as an example. When you're standing on the surface of the Earth, which we know is round, it's an oblate spheroid, right? So we're standing on the surface of the Earth, it appears to basically be flat if we get rid of all the hills and the valleys. The Earth appears to be flat, okay? And so if you're close enough to a curved surface, you fail to see the curvature. And that's why we make the areas infinitely small, so that we can consider it to be flat. Now, you of course know that this is probably leading up to calculus, and you would be correct. We are going to be using some calculus here in a minute. But mathematically, this is what we're doing. We are saying that phi is equal to e1.a1 plus e2.a2 plus ... Okay, we can just keep going with that forever. And a couple of quick notes. By definition, the normal is going to be positive away from the source. Okay, so it's going to be positive pointing outward. And that negative is going to be toward the source. So you might think of it as coming out of the surface for positive. And for negative, you would say it's going into the surface. And as you might imagine, we're not going to have 1, 2, 3, or even 100 areas to add up. We're going to have an infinite number of areas to add up. And that is integration. So basically what we have is this. Phi is equal to the integral of E dot dA. Now, what is the proper interpretation of E dot dA? What does this conceptually mean to us? Well, conceptually, what it's telling us is that the density of the field lines is indicative of the field strength. Okay, so this is the basic idea behind electric flux. It's just the amount of field which is enclosed by an area. It is absolutely central and key to our understanding of Gauss's law. You're going to see that using flux makes things a ton easier because we're dealing with a scalar quantity, and it allows us to find the electric field without using a lot of heavy calculus like we did whenever we had the short objects of a continuous charge distribution. So things like a small ring or a small length of wire or a disk or something like that. So the electric field is really an important concept, but keep in mind that it's easy to lose sight of the fact that really this is just another way of talking about forces. And that's something which is never brought up by instructors. And so you start to think that we got these really crazy concepts out there that how did they even know to come up with it? And all it is just another way of looking at forces.